Hey guys, it's Mrs. Drajewski. Today we are going to talk about the convergence of a power series. Previously, we were working with the ratio test, and with the ratio test, every bit of the convergence depended on the value of 1. In a power series, it's going to depend on the value related to x, so the x value that's in our function. When we have to relate to x, then what's going to happen is we're going to create an interval of values where our x value is going to determine whether or not we're going to converge. And this is going to create what we call a radius of convergence, an interval, if you will, where any x value upon that interval will actually converge your series. So if that radius of convergence is infinite, then we would say that the series converges for every single x value existing on the set of real numbers. If the radius is equal to 0, that means not really very much of a radius at all. That just means that your series converges only when x equals one particular value. I think that this little diagram might help. When I visualize x values that could work, I'm really thinking about an x value like here, we'll call that x sub 1, and here x sub 2. In between x sub 1 and x sub 2, we have every possible x value that will converge our series. We call this the interval of convergence. Now, smack dab in the middle is this b value. This separates like the halves of the interval of convergence, if you will. And we could say that the radius of convergence is this distance between b and x sub 2, or between x sub 1 and b. That's the radius of convergence. If you think about in terms of like a circle, the radius is like the distance from the center to the edge. It's the same thing here. It's just the distance from the center of convergence all the way to the edge of our interval. Okay, now it's important to note that your endpoints could either be included on the interval of convergence or not. And in fact, what I've noticed is that students will frequently calculate everything else and then they forget to check the endpoints. So don't let that be you. So here's our first example. First question asks us, for what value of x is this series convergent? And then they ask us to state the radius and the interval of convergence. Well, I'm actually just going to use the ratio test just like we did before. And I like the ratio test. So step number 1, I'm just going to compare the a sub n plus 1 to the a sub n. So I'm going to take the absolute value of x minus 3 to the n plus 1 power divided by n plus 1. And then we're going to divide it by the whole original piece. So that would be x minus 3 to the n power divided by n. Woo-hoo. Okay, so let's move forward and simplify. I can use my rules for exponents to kind of break this apart. I'm also going to use my division at the same time. So I've got x minus 3 to the n power multiplied by x minus 3 to the first power. And I'm multiplying by the reciprocal, so I'm going to end up multiplying by n. You could either put the 1 there or not, it doesn't really matter. Then we divide, and I've got n plus 1 times x minus 3 to the n. Okay, we got some simplifying we can do here. My x minus 3's to the n powers are going to reduce to 1. And let's see what I have left. I've got n times x minus 3 divided by n plus 1. You know, we're going to have to take the limit to do the ratio test anyways. So I can have a dividing by n party right now. So let's do that. If I divide everything by n, I'm going to get n divided by n times x minus 3. And I'm going to have n divided by n plus 1 divided by n. Now you might be thinking, Mrs. Drieski, why in the world didn't you divide both of these terms by n? Remember, this is a product, so we've got n times x minus 3. I could use the distributive property here and then divide both terms by n, and that would work. But don't you see how it's exactly the same thing as having it like factored out in the front here? It's kind of the way that the multiplication works. So I can simplify this, and I'm going to take the limit as n approaches infinity of, well, these will cancel out, leaving me with x minus 3 on top, and down below with 1 plus 1 divided by n. When I take the limit as n approaches infinity, this is going to give me x minus 3 divided by 1 plus a 0. So unlike last time when we were working with the ratio test, I'm going to get a result like this, the absolute value of x minus 3. This is not a constant. This is different. And in the ratio test, what we would do is we would take that constant that we would get and we would compare it to 1. But we're still going to compare this to 1. This series will be divergent if the absolute value of x minus 3 is greater than 1. But what I want to know is, where is it convergent? So I'm going to take the absolute value of x minus 3, and I'm going to set that less than 1, because in the ratio test, convergence happens when your value is less than 1. So it will be absolutely convergent if the absolute value of x minus 3 is less than 1. Now, back in the day when we were first learning all about solving inequalities and solving absolute value equations, we learned that because absolute value is the distance that a number is away from 0, this could either be 1 away from 0 in the positive direction, or it could be 1 away from 0 in the negative direction. So to work with absolute values and inequalities, we're going to use a compound inequality. I'm going to take -1, the distance in the opposite direction, and drop my inequality, or my absolute values rather. Now all I have to do to solve this is to get x alone. I'm going to use the opposite operation and move that 3 to the other side. Or I should say other sides, because we have 3 sides on this equation now, or inequality. So I've got -1 plus 3, which is 2. And I've got 1 plus 3, which is 4. So I know that x has to be a number that's in between 2 and 4. So it's going to be convergent between 2 and 4. And a lot of students would stop right there, and they will only get half of the problem right, because you also have to check the convergence at 2 and 4. The endpoints, they're important. So let's check out the endpoints anyways. What about them? So let's start with x is equal to 2. Then our sum would have been the sum to infinity of n equals 1 of 2 minus 3 to the n power all divided by n. I can simplify that. That's just the original problem with the 2 substituted in for our x. That's going to give me -1 to the nth power all divided by n. Now that's an alternating series. And we know that this alternating series is conditionally convergent because we have solved this problem numerous times before. It converges when it is alternating, but if we take the absolute value, then we're just going to get a harmonic series, and that would diverge. So it is only conditionally convergent. Now, what about if x was equal to 4? Then we would have the sum from 1 to infinity of 4 minus 3 to the n power divided by n. Well, that's just 1 to the n power divided by n. And 1 to the n power, doesn't matter how many times you multiply 1 by itself, you're still going to get 1. So this is just and this series is a harmonic series and it diverges. Notice the difference here. This does converge as long as it's just this series. But if we took the absolute value of it, it would be this series and that would diverge. That's why we called this top one conditionally convergent. But this bottom one, this just straight up diverges. The harmonic series, you could say that it fails by the p-test in the situation where p is equal to 1. It fails big time. So I'm just going to write down that it's a harmonic series. And it diverges. Now, if we go back up to the original question, it says to state for what values of x is it convergent, and then, hence, state the radius and the interval of convergence. Okay, well, we can do that. We know that it's convergent between 2 and 4. So I would say, give me like a statement, like the interval of convergence is 2 is less than or equal to x, which is less than 4. I use the equal to sign for the 2 because we're conditionally convergent at 2 for the endpoint. And I didn't use the equal sign for 4 because it diverges at 4. Another way you could write this is with this notation, if you like. So it asked for the interval of convergence, and we were also asked to find the radius. So imagine that. From 2 to 4, that whole entire distance is 2, right? But we're not looking for the whole entire distance, we're looking for the half distance. Remember, that's how radius works. It's not the diameter of convergence, it's the radius of convergence. So the way I would calculate it is just take your larger number, subtract the smaller number, divide it by 2. So we get 4 minus 2 is 2, 2 divided by 2 is 1, your radius of convergence is 1. And again, we can draw it all out. Here's 2, and here's 4 on our number line for x values. We can choose 2. We cannot choose 4. And our radius of convergence is this distance here, which is 1. And that is a power series. Let's move on. Let's try example number 2. So maybe you guys could try this one on your own. So go ahead and pause it, see if you can try it, and then you can maybe fast forward through the work and see if you got it right. So I'm going to start by using the ratio test. So that would be the limit as n goes to infinity of the absolute value of our a sub n plus 1 divided by our a sub n. So, everywhere I have an n, I'm going to put an n plus 1. And this one already has an n plus 1, so that'll be an n plus 1 plus 1. And then you divide by like the original. So we had negative 3 to the n, x to the n. Wow. Okay, so I'm going to simplify. I like to do my division and stretching out of my terms at the same time. Just saves me a little bit of space. So I've got negative 3 to the n times negative 3 to the first times x to the n times x to the first times, then my denominator here is the square root of n plus 1. Wowzers. Now, I've stretched out the top, stretched out the bottom. That's multiplying by the reciprocal. So I'm going to get these middles here. This is going to give me the square root of n plus 2, because 1 plus 1 is 2. Then I've got negative 3 to the n power and x to the n power, all inside the same set of absolute values. And we can reduce this. So negative 3 to the n and negative 3 to the n reduce, x to the n and x to the n reduce, and it looks like I have negative 3x times the square root of n plus 1, all divided by the square root of n plus 2. All right, so it'll be a lot easier for me to take the limit as n approaches infinity of all this stuff if I can reduce these n plus 1s and n plus 2s here so that the limit will go to 0 inside there. Hopefully you know what I'm talking about. So I'm going to have it dividing by n party, and I'm going to do that inside my radical. So I've got negative 3x times the square root of n divided by n plus 1 divided by n, and divided by the square root of n divided by n plus 2 divided by n. I'm multiplying by the same thing on the top and the bottom, just as we did previously. Oh my goodness, that was a terrible line drawn. I am still getting used to this pen, you guys. So I'm going to take the limit and also simplify here. So I've got negative 3x times the square root of 1 plus 1 over n. And we know that is going to be 0 when we take the limit, right? And we've got the square root of 1 plus 2 divided by n. Again, as we take the limit, as n approaches infinity, these guys are both going to become 0. Then I'll have the square root of 1 divided by the square root of 1. Please, you know what this is. This is negative 3x. Now, back when we were first doing the ratio test, we would compare it to 1. But now, I don't just have a constant here. I've got a variable x. So this is going to converge if the absolute value of 3x is less than 1. Okay, so I can solve this and make it a compound inequality. So I'll take negative 1 is less than negative 3x, which is less than 1. That just means that this could go in either direction, 1 away from 0. I'm going to divide both sides by negative 3. Now, when you divide an inequality by a negative, your inequality symbol is going to flip. So that is going to happen here as well. So I'm going to get negative 1 divided by negative 3. That's going to be a positive 1/3 and a flipped inequality. And positive 1 divided by negative 3 is a negative 1/3 and also a flipped inequality. Now, usually I like to have my smaller number written on the left-hand side, so I'm going to do that. That means I'm going to put my larger number on the right-hand side with the x in the middle. But you see how x is actually smaller than 1/3? We want to make sure that that symbol is still showing that it's smaller than 1/3. So 1/3 is larger than x. So I haven't changed anything here except for just the order that these are written in. And we also see that x is larger than negative 1/3. So we're going to make sure that it's still larger than negative 1/3. This is kind of like the classic way that we're writing our inequalities. So in order for this series to converge, x has to be a number that's in between negative 1/3 and positive 1/3, not a very wide radius of convergence. So now what we're going to do is we're going to check those endpoints. Does it converge at negative 1/3? Does it converge at positive 1/3? Let's find out. So let's start with negative 1/3. So I'm just evaluating these endpoints now. If x is equal to negative 1/3, then my series is going to look like this. I'm going to have negative 3 to the n power x, but that's really negative 1/3. And that's all divided by the square root of n plus 1. We simplify this. These both have the same exponent, so they can be combined together. So I will have negative 3 times negative 1/3 divided by the square root of n plus 1. Now these 3's cancel out, the 1's cancel out. This is just 1 to the n power, which is just 1. So I've got 1 divided by the square root of n plus 1. Now, as n gets really, really large here, this guy is going to be also, we're not taking the limit here. It's a sum, silly me. This actually kind of looks like a p-series. Do you see it? We've got like, well, let me make it a little bit more explicit. I have 1 divided by, remember the square root of n plus 1 is the same as n plus 1 to the 1/2 power. And this is actually going to diverge because we know that if our exponent is less than 1, that we are going to diverge. Okay, so now let's try when x is equal to 1/3, positive 1/3. Okay, so similar to what we had up here, our exponents are the same, so we can combine the bases, and this is going to simplify a bit, kind of nice. Negative 3 times 1/3 is negative 1. Now, this is an alternating series. In an alternating series, it converges if the limit as n goes to infinity of the non-alternating part goes to 0. So let's look at it. In this case, our b sub n, the non-alternating part, is 1 divided by the square root of n plus 1. This is not the series 1 divided by the square root of n plus 1. This is just the non-alternating part. So of the series, and this rule only works for alternating series, so don't confuse it. If the limit as n goes to infinity of b sub n is equal to 0, then it converges. This is the rule for alternating series. And that actually is the case. So as n gets really, really, really big, yeah, we're going to take the square root of it, and that will be in the denominator. It's going to go to 0. So it converges. All right, so if it diverges at negative 1/3 and it converges at positive 1/3, I believe we have our interval of convergence. So the interval, the IOC, the interval of convergence, is negative 1/3 is less than x, which is less than or equal to 1/3. And that radius of convergence is 1/3, because the distance from the middle to the edge is 1/3. And we're done. All right, let's try example number 3. We're asked to find the radius and the interval of convergence for this series. Okay, kind of classic styled one, something that, I don't know, a teacher might put on a math test, for example. So we're going to take the limit as n approaches infinity of, obviously we're going to apply that ratio test. So I should always make this bigger. The first one is always larger than I write it. So I've got negative 1 to the n plus 1 power times n plus 1 times x plus 3 to the n plus 1 power, all divided by 4, oh my goodness, to the n plus 1 power. Okay, and some more. The original now, that's going to be negative 1 to the n times x plus 3 to the n, all divided by 4 to the n. My, oh my. Let's simplify. Here we go. I'm going to stretch it out. Negative 1 to the n power times negative 1 to the first power times n plus 1 times x plus 3 to the n power times x plus 3 to the first power times 4 to the n. Because this is a complex fraction, I'm going to multiply by the reciprocal. And stretch it out. These middles are going to multiply together. That's going to be 4 to the n times 4 to the first times negative 1 to the n times n times x plus 3 to the n power. And the whole thing is being absolute valued. Goodness me. All right. So my negative 1 to the n's reduced to 1. I've got that 4 to the n. That is also going to reduce. I've got x plus 3 to the n power. Some more reducing there. My goodness, I think I can rewrite this now. Let's see what I got. I've got the absolute value of negative 1 times n plus 1 times x plus 3. That's not too terrible. All divided by 4 times n. Okay, okay. I think it's about time that we threw a party. Yeah, a dividing by n party. So let's get those n's ready to divide. We'll take the limit as n approaches infinity of the absolute value negative 1 times n divided by n plus 1 divided by n times the quantity x plus 3, all divided by 4 to the n. 4n divided by n. And reduce, and take the limit. Let's see. In the numerator, I'm going to be left with the absolute value of negative 1 times, well, this will go to 1. And it doesn't have any n's in it, so that's just going to stay x plus 3. And down below, that n canceled out, so that's not going to be affected by the limit anymore. So I'll probably write this as the absolute value of negative 1/4 times x plus 3. And we know that this converges when it is less than 1. So we could go ahead and try and solve that. So I'm going to write myself a little complex inequality. I have negative 1 is less than negative 1/4 times x plus 3, which is less than 1. I'm going to multiply both sides by a negative 1/4. By a negative 4. Multiply by the reciprocal. Here my 4's reduced, my 1's cancel out. Negative 1 times negative 4 is positive 4. Don't forget your inequality sign is going to flip because you multiply both sides by a negative. That'll do it. And this inequality sign is going to flip. And 1 times negative 4 is negative 4. Then what I have to do is subtract 3 to all sides. And I've got 1 is greater than x, which is greater than negative 7. And I like to have my smaller values to the left and my larger values to the right. So I'm going to rewrite this so it says negative 7 is to x is to 1. X is larger than negative 7. So I'm going to face my inequality the way it's supposed to be. And x is smaller than 1. Again, face my inequality as it's supposed to be. So this would be almost my interval of convergence. However, I do need to change it and check those endpoints. So will it converge at negative 7? Will it converge at 1? Let's check them out. So let's check those ends. Let's see. Let's start with x is equal to negative 7. If x is equal to negative 7, then I'm going to have the sum negative 1 to the nth power times n times negative 7 plus 3, all to the n power, divided by 4 to the n. Well, this is going to stretch out and simplify. That's going to give me, let's see, negative 1 to the n times times, well, 7, negative 7 plus 3 is positive, no, negative 4. All divided by 4n, 4 to the n power. And, these both have the same exponent, so I can combine them together. Negative 1 times negative 4 is positive 4, so it's going to be positive 4 to the n. Hey, I'm going to have a positive 4 to the n on top and a positive 4 to the n on the bottom. This is going to simplify neatly, so I have the sum from 1 to infinity of n. So, what do you think? To me, this looks like it's just going to diverge. It's going to keep on getting larger and larger and larger. So this is going to diverge. It's never going to end. Okay, very nice. So now let's test the other endpoint. Let's test where x is equal to 1. If that's the case, I've got negative 1 to the nth power times n times 1 plus 3 to the n power. Oh, that's nice. I'm saying that because I see right away that 1 plus 3 is 4, and 4 to the n is on top, and 4 to the n is on the bottom. My goodness, those are going to cancel out. And we get the sum from 1 to infinity. I don't know why my equal signs keep on ending up like that. I'll tell you what. And I've got negative 1 to the n power times n. That's an alternating series. And an alternating series will converge if the non-alternating part has a limit that goes to 0. But as we know, that limit is going to continue to grow and grow and grow. Therefore, that limit does not exist. This diverges. Remember, your b sub n has to have a limit as n goes to infinity of 0 in order for it to converge. And the limit as n goes to infinity of n does not exist. That's why it diverges. I love the alternating series rules. It's like probably one of the easiest ones. Okay, so we know that neither one of these endpoints converges. So that's going to make writing our interval of convergence pretty much a done deal. We know the interval of convergence is from negative 7 to 1, not including 7 and not including 1. And then we need to find the radius of convergence. So the radius, sometimes it's just easy to see what the radius is. Other times you should just do the subtraction. I would do 1 minus negative 7 divided by 2. 8 divided by 2 is 4. So your radius of convergence is 4. Bada bing, bada boom. That was kind of a fun one. All right. So, did you know that you could also differentiate and integrate power series? Yeah, it's true. You definitely can. We're just going to apply some of the rules. At first, you might think, oh no, this looks horrible. But this is just the power rule, guys. You already know how to do this. This is the power rule. The power rule looks complicated, but you're just subtracting 1 from your exponent, multiplying by the original exponent in the front to take the derivative. And to take the antiderivative, you add 1 to your exponent and you divide by the new exponent that you have. So it's actually not too bad. So in this problem, we've got example number 4 here. It's our last example. We're asked to take the integral from 1 to 1/10 of this power series. So just as a reminder, we actually already did calculate this series had an interval of convergence. We did this on problem number 2, I believe, and we figured out that the interval of convergence for this series was from -1/3 to +1/3. And so one thing that we should note is that in order to take the antiderivative, the upper and lower limits of integration have to be on the interval that the power series converges for. So maybe let's make a little note. Oh gosh, I was looking at my notes and not up here. So this is the series I'm talking about, that since this actually does converge in between -1/3 and +1/3, our interval of convergence also needs to converge there. Let's say we explored. Okay, so are they? Absolutely. Our lower limit of integration here is at 0, and 0 is in between -1/3 and +1/3. And our upper limit of integration is at 1/10, and 1/10 is in between -1/3 and +1/3 as well. So just in the setup right here, we definitely can do this because our upper and lower limits of integration are on the interval of convergence. If not, we wouldn't be able to calculate it and we'd be done. Of course, we're going to continue. So I'm going to take the antiderivative from 0 to 1/10 of -3 to the nth power times x to the n, all divided by n plus 1. Dx. Now, I know at first you're probably thinking, whoa, I'm not really feeling this. But this stuff right here doesn't have any x value in it. So this is kind of like our c sub n. It's like our constant. It's just going to give us a result, like a numeric result. So when we're looking at our formula, so we're taking an integral. Let's pop back over here a sec. We're taking the integral like we are here. That's just that c sub n value here, all that stuff. So we're going to divide it by n plus 1, and we're going to take x and we're going to raise it to the n plus 1. We're going to add 1 to the exponent. So if this is our c sub n and we're calculating the integral, let's go for it. Here we go. I have the sum from n equals 0 to infinity of this whole thing, so that's the constant, times x to the n power. So the next thing that we would do here is take our original and add 1 to the exponent, and then we divide by the new exponent. It's the same rule for integration as we've done a bazillion times. And we're going to calculate this from 0 to 1/10. Just like we did a bazillion other times, we're going to substitute in the 1/10 for the x and then the 0 for the x and subtract those two results that we've got. So I'm going to take that whole constant part, kind of set it to the side so I can do some multiplication there. Oh, wow, that's a sigma. do that substitution. So I'm going to have 1/10 to the n plus 1 power divided by n plus 1 minus 0 to the n plus 1 power divided by n plus 1. Okay, well, 0 to the anything power is 0, and 0 divided by anything is 0. So really all we have to worry about is this piece. I'm just rewriting it. Ah. And that's like pretty much what we've got here. We can simplify it, I guess, a bit more. We know the square root of n plus 1 is really an n plus 1 to the 1/2 power. And this n plus 1 is really n plus 1 to the first power. So the bases are the same. We can add our exponents. So this is going to give me -3 to the n power times 0.1 to the n plus 1 power, all divided by n plus 1 to the, well, 1 plus 1/2 is 1/2 or 3/2, or however you like to write it. And then don't forget, this is the sum from 1 or 0 to infinity. I think that's like as tidy of an answer as we're going to get. And that's it, we're done. Yay! All right, my dears. So that's what we've got. Please make sure that you go in and you do your homework. In this case, this is going to be the Power Series homework on MyLab and Mastering. But if you'd also like to do the problems from the textbook, that would be great. That's some nice extra practice. I think this is going to be day 8. From obviously Unit 12. Hopefully you understood Power Series and you enjoyed that. The next thing that we're going to be doing is some work on Taylor and Maclaurin series. So we're not done with series yet. I hope this has been fun, and I will talk to you next time. Bye, guys.